Hi, in the next concept in quadratic equations, we'll be looking at the idea of polynomials. So we've now looked at quadratic equations in a lot of detail, and we've also looked at the idea of a quadratic expression. So what we now want to do is we want to define, define a general polynomial function and then extend some of the concepts for quadratic equations to higher degree polynomials, right? So let's go ahead with that. So in the first class itself, I had defined a general polynomial equation in degree n, and corresponding to that, we can now talk about a general general polynomial function of degree n. So we've already used the f of x notation. So if f of x, a general polynomial function of degree n, could be taken in this particular form, so a n x n plus the values a n minus 1 up till a1, a0, etc. as discussed before. For the time being, we'll assume that they belong to the set of real values. The coefficients, again, you could also define a polynomial function for non-real coefficients, but at the moment we'll be restricting ourselves to real coefficients. And of course, if you want to call this a polynomial function of degree n, you'll have to impose the condition that the leading coefficient, that the coefficient of x raised to n must not be 0. So an over here is not 0, right? So this then becomes a function. This then is a function of this particular form, where n of course is a natural value, becomes a polynomial function of degree n, right? So again, as some simple examples, so f of x equal to 2x minus 1 is a linear function of x. Similarly, g of x equal to x square plus x minus 1, as we've already seen, is a quadratic expression in x, and h of x equal to maybe x cube plus 2x cube plus 3x square plus 1 happens to be a cubic expression in x, and you can similarly keep on defining higher degree polynomials. Now, two very key concepts which are associated with polynomials are something known as the remainder theorem and something known as the factor theorem. The remainder theorem being a more general result, special case of which happens to be the factor theorem. But before we go into the remainder theorem and the factor theorem, it is important to understand the idea of polynomial division, right? So let's just look at that. So polynomial division, the structure of polynomial division is kind of similar to the way you talk about division of numbers. So similarly, so for example, when you talk about 7 being divided by 3, 7 is the dividend, 3 is the divisor. So 7 when divided by 3 will give you a quotient of 2 and a remainder of 1. So in other words, 7 is equal to 2 times 3 plus 1. Right? So again, the dividend 7 when divided by the divisor 3 gives you a quotient of 2 and a remainder of 1, right? So dividend is quotient times divisor plus the remainder. So division of polynomials will follow a similar structure. So the idea is that, again, if you have a polynomial f of x and you divide it by a polynomial g of x, another polynomial g of x, you'll get a certain quotient q of x and a certain remainder r of x, both of which will be polynomials. Here we are of course assuming that the quotient, that the degree of the numerator, the degree of f of x, is greater than or equal to the degree of g of x, right? And this basic structure is then again followed, that the dividend is quotient times the divisor plus the remainder, right? So let's just quickly look at this. We'll just write it down. Right? So again, what we are saying is that we are starting off with the polynomial f of x and we are dividing it by the polynomial g of x. And again, we are assuming here that the the numerator over here, the f of x, that the degree of f of x is greater than or equal to the degree of g of x. So then in that case, we'll have these polynomial functions q of x and r of x, where q of x, again, we refer to it as the quotient and r of x is the remainder, such that this statement will be identically true. Identically being true, the statement being true identically obviously means that the statement will be true for all values of x, right? Now again, so just to emphasize, it's quite similar to what happens when you're kind of dealing with division in case of natural numbers or integers for that matter. Or I mean division in for numbers in general. Now, two very important observations are regarding the with regards to the degree of q of x and r of x, right? So one thing that you can always say about the degree of the quotient of q of x again over here is the quotient, and r of x over here is the remainder. So one thing that you can always say about the degree of the quotient and degree of the remainder is as follows. The degree of the quotient will always turn out to be the same as the degree of the dividend minus the degree of the divisor. So basically, if you're dividing a fifth degree polynomial by a second degree polynomial, what you can definitely say is that the quotient will be a polynomial of degree 3. As regards to the remainder, what you can all say is that the degree of the remainder will be less than the degree of the divisor. So the degree of r of x will have to be necessarily less than the degree of g of x. So which again means that if you're dividing a fifth degree polynomial by a second degree polynomial, the remainder will have a degree of less than or equal to 1. The reason that we are not specifically saying that the remainder is equal to 1 is that the degree of the remainder in this example is equal to 1 is that, of course, there could be a special circumstance in which the remainder itself might turn out to be a constant itself, right? So in general, for the remainder, what we can say is that the degree of the remainder will be less than the degree of the divisor. Right, so let's just quickly verify this by a quick long division. Long division is something that you're already familiar with. So let's just quickly look at this as an application. Before we go into the example, another important a couple of points that we should definitely quickly observe are these. First, from the given fact that the remainder will always have a degree of less than the denominator, will always have a degree less than the divisor. A special case arises where the divisor itself, where g of x itself happens to be a linear function, right? So if g of x itself is a linear function, then that makes its degree equal to 1. And also further, you're saying that the remainder has to have a degree of less than the divisor, which means that the remainder will have to have a degree of less than 1. Now less than 1 in this case can only mean that the degree is 0, which would mean that the remainder is a constant. So one important observation is that when any polynomial is divided by a linear function, the remainder will always necessarily be a constant value. It will be independent of x. So if and similarly, if the remainder, if the divisor happens to have a degree of 2, which means that g of x is a quadratic expression. In that case, what you can say is that the remainder will in general have the form so if g of x itself is a quadratic expression, then what we can say is that the remainder r of x will itself have the form px plus q, where p itself could also turn out to be 0. Okay? For that matter, even q and p simultaneously could be 0, in which case you would say that the remainder happens to be 0. Okay? And one last idea is that when will we say that, just in case of numbers, when I say that 6 is divisible by 3, what I mean is that the remainder left on that division happens to be 0. Similarly, in case of polynomials, I'll say that the polynomial f of x is divisible by the polynomial g of x if the remainder left on after division happens to be 0. Another way of expressing the same idea is to say that g of x is a factor of f of x. So let's just take a quick example for basic polynomial division. Right, so in both these examples, we have been given the dividend and the divisor g of x. The dividend is f of x and the divisor is g of x. and in both cases you want to find the quotient q of x as well as the remainder, right? So again, some things which we can immediately say are that in the first part, the quotient itself will definitely be a polynomial of degree 2, and the remainder will be some constant value. And for the second part, similarly, we can definitely say that the remainder will again, the quotient will again have a degree of 2, and the remainder will in general either have a degree of 1 or it might turn out to be a constant. Okay. So let's go to the first part. So again, long division is something which you've seen in earlier classes. We'll just quickly recap it. So in the idea of long division is that you successfully keep on applying the same sequence of steps. We'll first divide the highest degree term of the dividend and the highest degree term of the divisor. Multiply these expressions and subtract. Right? So when you subtract, you'll get a minus 3x squared. This comes over here. Again, divide these two, so you get minus 3x. Subtract, again divide these two, subtract. Now at this stage, obviously the division will necessarily have to stop. Let's just check our calculations again. X cube minus x square plus x plus 1 square, x cube plus 2x square. Subtracted, so I got a minus 3x square plus x minus 3x square by x, so that's a minus 3x minus 3x minus 6x. Subtracted, I got a 7x plus 1. So in this case, as we had, so the remainder at this stage, obviously your division will have to stop because I mean you've reached a point where this expression has a degree less than the divisor, so obviously the division cannot go further. So finally our analysis is that the quotient is this polynomial and the remainder happens to be minus 13. So an identity which we can express is that, again, fx is q of x into g of x plus the remainder. Again, this is something which should hold true for every value of x, and we can easily check that for some simple values. So if I were to put x equal to 0 on both sides, I get 1 over here. Over here, I get 14 minus 13, which is again 1. Similarly, if I put x equal to 1, I get 2 over here. Over here, I get 7 plus 1, 8 minus 3, 5. 5 into 3, 15. 15 minus 13 is 2. And you can, in fact, be absolutely sure that for every value of x, the LHS and the RHS will turn out to be exactly the same. Right? So just take a minute and try the second part on your own. Again, it's pretty straightforward. Now, in the second example, we'll have to be careful, and we have to account for the fact that you have some missing coefficients over here, right? So it's better to kind of deal with the problem in this way. So you have a 0x cube plus 1 times x square, right? So again, highest degree term, when I divide them, I'll get a 2x square. So when I multiply, I get a 2x raised to 4 minus 2x cube plus 2x square, which when I subtract, I get 2x cube minus x square plus 0 times x, which is brought down. Right? Again, highest degree divide, so I get a 2x. Sorry, plus 2. 2x cubed by 2x squared by x squared gives me 2x, so plus 2x, so 2x cubed minus 2x squared plus 2x, which again if I subtract I'll get a x squared minus 2x, and the minus will come over here. Finally I have a plus 1, so that's x squared minus x plus 1, which again if I subtract I get a minus x minus 2. And of course at this stage our division will stop. So the quotient again is 2x squared plus 2x plus 1, the remainder is minus x minus 2, which turned out to be a linear function. So again an identity that is always going to be true is that so this again must be an identity, which we can again quickly check for simple values. If I put x equal to 1, I get minus 1 over here, I get 1 minus 2 minus 1 over here. If I put x equal to 1, I'll get 2 over here. For x equal to 1, this becomes 5, 5 minus 3, 5 minus 6, 2 again. Right, so this covers the idea of polynomial division. So now one important result which follows from the division algorithm for polynomials is something known as the remainder theorem. So the remainder theorem says that if you have a polynomial f of x and you divide it by x minus a, so you divide it by some linear factor, then the remainder can immediately be found. You don't actually have to go through the whole process of long division, and that remainder simply is the function value at a. A over here effectively represents the root of the linear factor. So the divisor, wherever it's becoming 0, take that value of x and substitute it into the dividend, the function f of x. You'll finally get f of a again from the notation that we've seen. F of a corresponds to the function value of the polynomial at x equal to a, which will be obtained by replacing x by a and calculating whatever value that you're left with. So the remainder theorem again, it's a straightforward result, but again it's important. So it's essentially again to repeat what it's saying is that to find the remainder you don't actually have to go through that entire process of long division, right? You simply just kind of calculate the function value at the root of the divisor. So let's just quickly verify this with an simple example and then go on to its proof. So as an example, suppose we have f of x is, so suppose our function value is the function is x cubed plus x squared plus x minus 1, and the dividend is x plus 2, right? So you're dividing f of x by g of x and you want to quickly figure out the remainder. So let's just first use our original way of the old basic method of long division, and then we'll see how the answer can be found in a much quicker way. Right. So now again, if we So if we continue with the long division as we've discussed before, the remainder is going to be minus 7. Now let's also find out the function value at minus 2. Why we have chosen minus 2 is because minus 2 is the root corresponding to g of x. So if I substitute x equal to minus 2 over here, what do we get? Minus 8 plus 4 minus 2 minus 1, which is minus 7. So that's what the remainder theorem was saying, that if you had wanted to find the remainder when f of x is divided by this linear function x plus 2, you don't actually have to go through long division. You can simply substitute x equal to minus 2 in the polynomial, and the value that you get will be the remainder, right? And of course, over here, the example we had seen was a simple one, in which case you were just dividing a cubic. So you could even have had used up long division to get the result. But imagine a situation in which you have a 10-degree polynomial and you're dividing it by maybe a linear function. So the process of long division will definitely take a longer time, and simply finding the value of the function at a specific value as such will not be take up as much time. Right? So let's just quickly try to come up with a proof for the remainder theorem. So the proof of the remainder theorem again is something which is very straightforward. We just have to use the division algorithm. So if you go to the division algorithm, this statement must corresponding to f of x and x minus a, there will be a quotient q of x and the remainder r of x. And we already know now that the degree of the remainder has to be less than the degree of the divisor, which means that the degree of the remainder will have to be 0, which means that because the divisor itself is a linear function, which means that the remainder will necessarily have to be a constant. So first of all, we already know that so r of x is definitely some constant, call it k. So again, our identity becomes right. So this statement then is our identity, which means that again it is true for all values of x. Specifically, suppose we put x equal to a in this identity. So we get f of a is q of a times 0 plus the value k. K is a constant, so its value will remain the same. So interestingly, the value of k therefore turns out to be the same as the function value at x equal to a, which completes the proof. Now, using the remainder theorem, from the remainder theorem, we can get something known as the factor theorem, which will talk about the condition under which polynomial f of x will have. How do you check whether a given linear expression is a factor of a given polynomial or not? So the idea now is very simple. I'll say that x minus a happens to be a factor of f of x if and only if f of a itself happens to be 0. That is to say that the function value at x equal to a happens to be 0. This really doesn't require any proof. We just need to know what do you mean by x minus a being a factor. So as already discussed, when I say that x minus a is a factor of f of x, or in other words that f of x is divisible by x minus a, you're basically saying that the remainder must be 0. But we've already seen from the remainder theorem that the remainder should have been the function value at a. So if you want x minus a to be a factor of f of x, the remainder which is f of a must obviously be 0, right? So the factor theorem, of course, it happens to be fairly straightforward, but it kind of now provides you an important link between roots of a polynomial and factors of the corresponding polynomial expression. So again, it's a simple idea, but it's important to understand it. So the way I can establish the link is this. So if x equal to a, so this is one idea which is, this is one idea which is important. So if I say that the value ax, if f of x equal to 0, if it is a polynomial equation and x equal to happens to be a root of that equation, then what I can equivalently say is that x minus a then must be a factor of f of x. Right? Again, this doesn't really require any proof. When I say that x equal to a is a root of f of x equal to 0, what that would require is that f of a happens to be 0. But if f of a is 0, then by the factor theorem, x minus a must be a factor of f of x, right? So as an example, if you recall, we had seen this idea of sum of roots and product of the roots. So we had shown that for ax square plus bx plus c equal to 0, if the roots are alpha and beta, then the sum of the roots alpha plus beta happens to be minus b by a, and the product of the roots happens to be c by a. The way we had proved this was simply to actually plug in the values of the roots from the quadratic formula. Using the factor theorem, there's an alternate way to approach the to kind of prove the relation between the roots and the coefficients. And this alternate way is kind of important because it can be extended to higher degree polynomials also. So again, let's say that alpha, beta are the roots of so from what we have discussed, x minus alpha and x minus beta both must be factors of the quadratic expression ax square plus bx plus c. But the fact that x minus a, alpha and x minus beta are factors of it would have to mean that ax square plus bx plus c as an expression is equal to x minus alpha into x minus beta into something else also, right? So there might be something else over here. But when I'm expressing ax square plus bx plus c, x minus alpha and x minus beta obviously have to be there in terms of its factors. Now if we note, we kind of have to figure out what this question mark is. So one thing that we can directly say is that it has to be it can at most be, it has to be some constant only, because when you multiply these two expressions itself, you'll get a polynomial equation of degree 2. Obviously the left hand side, the right hand side has to be a polynomial expression of degree 2 only. And as far as the constant is concerned, we just have to observe the highest degree coefficient. When I multiply these two brackets, the coefficient of x square will be 1, whereas it's a over here. So clearly the constant over here has to be a. So as a consequence of the factor theorem, I can now say that ax square plus bx plus c must be identically equal to this expression, right? And now all I have to do is open up the brackets. And since these two, whenever I say that two polynomials are equal identically, the coefficient of each power of x on both sides will have to be the same. So what must happen now over here is that b must be equal to minus a times alpha plus beta, which gives me that alpha plus beta is minus b by a, and similarly c by a must be alpha into beta, right? And again, as I said, the good thing about this approach is that we can now use this to develop the relation between the roots and roots of a, for example, we can talk about the relationship between the roots of a cubic and the coefficients of the corresponding cubic expression, right? Which is something we'll be touching upon in some time. So let's just first quickly see some applications based on the remainder and factor theorem. Right, so both these problems are from the CCP. In the first question, the first thing that we'll have to figure out is the value of a. So for the first question, the first thing that we'll say is that since f of x is divisible by x minus 1, f of 1 must be 0. So imposing that condition gives us the value of a. So in fact a turns out to be 0. So f of x itself is . And now the question is that you want to find the remainder. You want to find the remainder when f of x is divided by x minus 2. For that, by the remainder theorem, we simply have to replace x by 2. Right? So f of 2 itself is . Right? So f of 2 itself is turning out to be 0, which obviously then also means that f of x is also divisible by x minus 2. In the second one, again, it's a simple problem, but it's important to understand this information. We are saying that f of x is divisible by a quadratic expression x square minus x. So it's important to understand how can this information be used, because now there are two unknowns a and b, so we will effectively need two conditions. So the only important thing to realize in the second question is that when we say that f of x is divisible by a quadratic expression, then f of x must also be divisible by, it essentially has to be divisible by both the linear factors of the quadratic expression of g of x, right? So over here x square minus x itself is easily factorizable, so it's x minus 1 times x. So since f of x is divisible by x minus 1 into x, it has to be divisible by x minus 1, and it also has to be divisible by x, right? So f of x is f of x has to be divisible by x minus 1, which also means that f of 1 has to be 0. So that gives us one condition. And similarly, since f of x is divisible by x, f of 0 must also be 0. Right, so the second condition simply gives b as 0, and a plus b was already 0. So a and b both will have to be 0, which means that f of x is simply x cubed minus x squared. And now we've been asked f of 2, so f of 2 must be 8 minus 4, so that is 4. Now this problem is slightly tricky, so we'll have to be careful in the way we deal with it. So again, we've been given a 4th degree polynomial, and we are dividing it by a quadratic expression, and the remainder is given to be 4x plus 3, and we want to figure out the values of a and b, right? So let's actually go back to our division algorithm. So now by the division algorithm, there must have been some quotient q of x. So right, so again, by this information that has been given, according to the division algorithm, this must be true, right? Dividend is quotient times the divisor plus the remainder. Now, the thing again we have to keep in mind is that q of x is not, we really don't know anything about q of x. The only thing in fact we do know about q of x is that q of x itself is a quadratic expression. But over here, to find the values of a and b, we don't actually need to know the exact quadratic expression that q of x is. We only need to observe that x square plus x minus 2. First of all, again, this is an identity. So LHS and RHS are equal for all values of x. And x square plus x minus 2 itself is factorizable as x plus 2 into x minus 1. So suppose I put x equal to 1 in the first equation. Since it's an identity, the LHS becomes a plus b, 5 minus 1, 4 plus 4. Q of 1 times 0, this entire term becomes 0 plus 7. So we don't actually need to know the value of Q of 1 because this product is anyway becoming 0. So I get one equation in a and b, which is a plus b is equal to 3, statement 2. And similarly, another value of x, I can theoretically I can put any value of x on both sides, but for example putting x equal to 0 doesn't help me because then I'll be stuck with the Q of 0. So now I can put x equal to minus 2 on both sides. So what does that give us? 16a minus 8b minus 2, right? So minus 4, that's minus 8 plus 3 minus 5 is equal to, this again becomes 0, and I put x equal to minus 2, so that's minus 5. So I actually get that divided by 8, so 2a minus b is equal to 0. And now I can easily solve the second and the third statement simultaneously. So when I put b equal to 2a over here, I'll get 3a equal to 3, so a is 1 and b must be 2, right? So I get a as 1 and b as 2. Right, so this again is a little tricky. This problem is a little tricky, so we'll have to be careful in how we deal with it. by a monic polynomial, we simply mean a polynomial whose leading coefficient happens to be 1. So the highest degree term will have plus 1 as its coefficient. That's one thing. And this information has been given. When divided by these three linear factors separately, we've been given the individual remainders. And on the basis of that, you want to figure out the remainder that will be left when you divide by x minus 7. Okay. So in this question, we'll introduce another polynomial g of x and we'll define it in this way. So again, an observation about f of x is that, for example, if you think about f of x by the remainder theorem, f of x first of all, by the remainder theorem, this is something that we can say. Since f of x when divided by x minus 2 gives you a remainder of 1, therefore f of 2 must be 1, right? And similarly, f of 3 is 2, f of 4 is 3, f of 5 is 4, and f of 6 is 5, right? But how can we possibly use this information to talk about f of 7, right? So an interesting observation is that suppose I define a new polynomial g of x as f of x minus suppose I decide to define this polynomial g of x as f of x plus 1 minus x. How does this help? So for example, now what would g of 1 be? G of 2 be? G of 2 will be f of 2, which is 1 plus 1 minus 2, that is 0. Similarly, g of 3 will be 2 plus 1 minus 3, which is again 0. And you can easily verify that g of 4, g of 5 and g of 6 all turn out to be 0. Right? So this was an very important step. By observation, I defined a new polynomial g of x. The reason why g of x becomes important is that effectively now, for g of x, what is happening is that at 2, 3, 4, 5 and 6, at all these 5 values, the function is becoming 0. But that by the factor theorem now will have to mean that g of x has at least these 5 factors for sure. X minus 2, x minus 3, x minus 4, x minus 5 and x minus 6. So therefore, g of x has to have the form sum h of x times x minus 1 x minus 2, and g of x itself was f of x plus 1 minus x, so f of x must have the form So now what we've been able to conclude from this information that was given is that f of x has this particular form. Right? So, but now to find out f of 7, we'll also need to know something about h of x. But for that, there were a couple of things that were given in the problem. The first thing that was given was that you want to find the minimum possible, you want to find a polynomial of least possible degree. Now the least possible degree thing clearly means that h of x should be some constant. Since you want that the degree of f of x should be the least, h of x clearly should be a constant. If h of x is a constant, then f of x will have a degree of 5, and if h of x is linear, it will have a degree of 6 and so on, right? So that's the first thing. And the second thing that's been given is that f of x is a monic polynomial. Now monic polynomial means that the degree, the coefficient of the highest power of x has to be 1, for which h of x also has to be a constant, and that constant specifically has to be 1. X has to be chosen as the constant function 1, which means that f of x must be equal to x minus 1 plus and now that we have the form of f of x, we can easily find out the function value at any given value of x. So f of 7 has to be found out. So that must be 6 plus So our final answer is 126. Right, so an important aspect of polynomials now is the idea of extending the relationship between roots and coefficients for higher degree polynomials. For us in high degree polynomials, the most important case for us is a cubic. So let's look at the case of a cubic separately first. For a cubic, we have these results. So suppose alpha, beta, gamma happen to be the roots of this polynomial, this cubic equation of degree 3. So these are the two things we can say. The first thing, as in case of a quadratic by the factor theorem, this polynomial must be identically equal to a times x minus alpha, x minus beta, x minus gamma. Proof is quite straightforward. Since alpha is the root of this equation, x minus alpha must be a factor. Similarly, x minus beta and x minus gamma must be factors. And they can, and of course additionally over here the product will have the coefficient of x cube as being 1, whereas the coefficient of x cube on the left hand side is a, so you'll have to kind of multiply the RHS by a to balance it out. If you multiply, when you expand the RHS and you compare the coefficients of the same powers of x on both sides, we can easily get these three relations. So these three relations are important. The first one talks about the sum of the roots. So sum of the roots of the cubic is given by minus of b by a minus coefficient of x squared by coefficient of x cube. This is the sum of the product taken two at a time, that is c by a. Similarly, product taken all at a time would turn out to be minus d by a. So all these three relations are important. These three again then constitute the set of elementary symmetric functions in alpha, beta, gamma in three quantities. If you want, again, you can keep extending this idea. So for example, for a fourth degree equation, this is what is going to happen. You have a fourth degree equation, suppose its roots are alpha, beta, gamma, delta. Then again by the factor theorem, this must be an identity, first thing. Second thing, sum of the roots taken one at a time will be minus b by a. Sum of products taken two at a time will be c by a. Sum of product taken three at a time will be minus d by a. And finally, sum of the product taken four at a time, which effectively is the product of all the roots, will be e by a. And this again can be, you can keep on extending this idea for all higher degree polynomials. And one last idea is the idea of transformations that we had discussed for quadratic equations. They can again be extended to all higher degree polynomials. So again, the two specific transformations that we had discussed, that if you want to reciprocate the roots, and the second, if you want to the roots to undergo a linear transformations. For them, what we could say is that. Right, so these are the two basic transformations that we had discussed for quadratic also. So if f of x equal to 0 is a polynomial equation, it has a degree n, and suppose alpha 1, alpha 2, alpha 3 up till alpha n happen to be the roots, then if the equation whose roots will be 1 by alpha 1, 1 by alpha 2 up till 1 by alpha n will simply be obtained, is simply given by f of 1 by x equal to 0. That is to say that in the original equation, all you have to do is replace x by 1 by x. And similarly, if you want the roots to undergo specifically a linear transformation, p alpha 1 plus q, p alpha 2 plus q, up till p alpha n plus q, right? So every root has been multiplied by or divided by a factor of p, and q has been added to it. Of course, q would be positive, and p could also be less than 1. So in that case, all you have to do is, so your required polynomial in that case is f of x minus q by p equals 0. So from x subtract q and divide by p, and replace x by x minus q by p equal to 0. So let's say we have this particular problem related to a cubic. We've been given the factors. Of this polynomial, and you want to figure out this. You want to kind of simplify this entire sum, right? So again, as a first step, so let's use the idea of transformations. Suppose I call beta plus gamma as alpha dash. So alpha plus beta plus gamma from here must be 0, since the coefficient of x square is 0. So that gives me that beta plus gamma must be minus alpha. Right. So the sum that you want to find out is actually 1 upon alpha plus beta, therefore becomes minus gamma, and beta plus gamma becomes minus alpha, and gamma plus alpha becomes minus beta. So that is minus common. Right. So now this of course is the sum of the product taken 2 at a time, which from what we've discussed will be 4. And this is of course the product of all the roots, which from what we've discussed will be 1. Minus 1, sorry. So our required answer is 4. So this completes the concept on polynomials. Thanks.